Just carrying on with our look at quadratic functions, because they are quite important. The linear function and the quadratic function, real important. So there's the most basic quadratic function of them all, y equals x squared, of course. And as I say, they're so important, and that's why. They're basically the building blocks of every polynomial, because every polynomial can be factorised down to be a combination of linear and quadratic factors. And that's why being able to solve these things, well, I mean, linear functions quite easy to solve, but being able to solve quadratics becomes very important. So as I say, the most basic one, x squared, and just like we saw with the basic straight line y equals x, every single quadratic can be built from it using translations, rotations, reflections, or combining all of those. How do you recognise a quadratic? Well, there's our general form, ax squared plus bx plus c. And we notice, oh look, 1's to the power of 1, and then the highest power of 1 is 2. Now, normally we say it's y is x squared, but it doesn't have to be, of course. You could have a parabola on its side, and it's the other way around. Now, a couple of techniques. First of all, using completing the square. So we could factorise our quadratic down like so. A outside x minus h squared plus k. And when it's in that format, it becomes very useful because we get the vertex straight away. So the vertex would be h and k, and that's all to do with shifting the curve. And we can read from that how we've shifted it. Where's the vertex gone to? The a, of course, still tells us what happens with the concavity. This is the same example as yesterday. No, we're not going to sketch it again, but how I would use the completing the square idea to solve the same problem, find those features. So x squared plus 8x plus 12, I want to complete the square. I know that when we complete the square, we'll end up with x and then half the coefficient of x all squared. So this one would be x plus 4 all squared. And of course, that gives me 16. So to bring it back to 12, we get negative 4. So now it's in that format, I can just look at that and say, well, the vertex is minus 4, 4. So that's one advantage of completing the square. If I want to find the x-intercepts, seeing I've got it in that form already, we still solve equals 0, but now all I've got to do is move the 4 to the other side. I've got something squared equals 4, so it must be plus or minus 2, and we get our x-intercepts that way. This example we looked at yesterday, write down the quadratic with roots 2 and 8, and they told us the vertex is 5, 3. So we know what the vertex is. I can say, well, I know it's going to take that form. Some constant times x minus 5 all squared plus 3. We know it goes through 2, 0 and 8, 0. I only need to use one of them. Which one did I use? I used 2, 0. Sub it in, and we get k equals minus a third, same as we did yesterday. So therefore, there's the equation. If I expanded it all out, we'd find, yes, we in fact get the same equation as yesterday. So that's completing the square idea. Another useful way of looking at quadratics is using the discriminant. And the discriminant is that bit under the square root sign in the quadratic formula. Called that because it discriminates between different types of quadratics. So b squared minus 4ac. There's your vertex. Now minus b on 2a, I'm sure we all knew, acts as symmetry. I don't know whether you're aware of the y value. The y value turns out to be minus the discriminant on 4a. Now that's useful to know because if we've just got a quadratic and they just ask to find the maximum or the minimum, I don't need to find the x value. I can just go, oh, well, minus the discriminant on 4a, that'll tell me the maximum or the minimum. And, well, of course, the x-intercepts or the zeros would end up being minus b plus or minus the square root of the discriminant because we said the discriminant was the bit under the square root sign. A couple of things to note here, though, and this is where the discriminating comes into play. If that discriminant turns out to be 0, then we know we've got no solutions because we can't find the square root of a negative number. So that means it's got no x-intercepts. Equals 0 means there's only one solution, so it must just touch. So I've called it one x-intercept. Is it correct to say it's an intercept? It's actually touching, it's not actually cutting the axis. And if it's greater than 0, we'll get two solutions. So yeah, it'll have two x-intercepts. That can be very useful, especially if you're looking at it and trying to solve a quadratic. If you're unsure, find the discriminant, and if it turns out to be negative, you know you've been wasting your time. There are no solutions. All right, same example. X squared plus 8x plus 12. Work out the discriminant, it's 16. So therefore my vertex is minus 8 on 2, minus 16 on 4, which is minus 4, 4. A little bit more about the discriminant. It tells us a lot more actually. It can also tell us whether the roots are going to end up being rational numbers or irrational numbers. So if the discriminant is greater than 0, what we should end up with is two different real roots. Okay, so we're going to get real numbers. They're going to be different. There's going to be two of them. As I say, it'll cut the x-axis twice. Discriminant equals 0. Now I said there was one solution, but there are still two roots. They just happen to be the same. So we still end up with real roots because we can get a solution, but they will be two equal real roots. And that's where it just touches the x-axis. And then we get the situation where it's less than 0, and at this stage we'll simply say there's no real roots. It does still have two roots. All quadratics have two roots. It just turns out that these ones are imaginary if they're less than 0. But as I say, we won't worry about that at this stage. So as far as we're concerned, there are no real roots. It never touches the x-axis. Keep on going. Well, if the discriminant is a perfect square, then the roots must be rational, because if it's a perfect square, we can find the square root. So we'll get a rational number. So describe the roots. 2x squared plus 6x minus 3. Well, let's find the discriminant. 60. Well, 60 is a positive number. So I know that there are two different real irrational roots. That pretty much covers everything. There's two of them. They're going to be different. They're going to be real, and they're going to be irrational. Find the values of k if this particular one has no real roots. Well, if it's no real roots, discriminant is less than 0. And by the way, when you're setting your working out, write that line. Unreal roots occur when discriminant is less than 0. Remember, you are presenting a solution for someone else's benefit, not your benefit. So they will want to know, well, why? Why are you making this less than 0? What is your logic? So you explain yourself in your solution. Okay? I know this fact, therefore, or i.e., that is, I can say minus 4 squared minus 4 times 2k. We solve that, we get k is greater than 2. K is greater than 2. Okay, that'll do us for today.